So this whole topic came about from the question that I've heard over the years from many people, some of them visiting this building: is computer vision just a perfect technology for blind and visually impaired people? And some people were surprised that computer vision wasn't the main sort of tool that blind people use. It sounds like a great idea. Computer vision has so many capabilities, and that's part of what we're talking about today. But obviously, it's just not that simple. Something that several people have talked about a bit today: if you're blind, how do you know where to aim the camera in the first place if you're looking for a target? Limitations of computer vision algorithms and systems. Sometimes they'll tell you things that are there, they'll hallucinate things that aren't there, they won't find things that are there, or they may misrecognize something. And then even if the computer vision component of a system works perfectly, how do you communicate those results effectively to a user? You want to perhaps provide audio or haptic feedback in a way that doesn't distract from other activities that the user is engaged in. And that's another separate sort of challenge. And so this talk addresses three particular applications that sort of case studies, in some sense, of these issues. And I'm going to talk about the first application on reading barcodes, and Roberto will talk about the second two. So the motivation, and we've seen some of this from Vladimir and other people. Maybe you're a blind person, you have two cans in your pantry, and you want to know which is the can of beans and which is the can of soup. And of course, there are dedicated scanners, barcode scanners, that are super reliable and very easy to use. But as dedicated equipment, it's not always that convenient. How well can you make a smartphone barcode reader work? And that was sort of the motivation for this project. And just to talk about some of the existing applications out there, there are a variety of barcode scanning apps, and most of them on the market are intended for people with normal vision. Red Laser, ZXing, etc. Come to mind. They usually assume that you know how to center the barcode in the field of view of the camera pretty nicely. And there are even a few apps, commercial apps already, that are expressly designed for visually impaired users, like Digitize, is sort of the one that I was most familiar with. But until recently, there weren't any commercial apps that provided feedback to help you find the barcode. So what Vladimir was talking about before, barcode localization. So you have to find the barcode before you can read it. And that basically is kind of a big chore for the user, especially if you're totally blind. You may have to scan the entire surface of a package just to find the barcode, and that can take a while. And just to mention, Vladimir, some of what he spoke about today and some of his earlier work as well has informed this. So that was one thing that motivated the development of this project we call BLADE, Barcode Localization and Decoding Engine. And this is joint work by Endo Taken, who's sitting in the back here, David Vasquez, you've already met, and me. And so we wanted to make a barcode reader that provided feedback to help guide the user to the barcode, and also to release this reader as an open source app. And just very quickly, we devised a user interface. The app is quiet if it doesn't think it sees a barcode. If it thinks there's a barcode visible in the camera's field of view, it makes a sound. And this will happen even if the barcode is only partially visible, or perhaps it's visible but not readable. And the particular information we provide is in two forms: volume and the continuity of the tone. The volume of the tone tells you how far you are to the barcode to help you get the right distance. The continuity, which could be a stuttered tone or a continuous tone or something in between, conveys how well centered the barcode is in the field of view. And there's not even time for a demo or a movie, but just very quickly to talk about some experiments. We tested this with 5 volunteer participants who were completely blind, and we had 18 products. And we just wanted to compare the performance of the person using this app, either using this audio feedback, switching it on versus switching it off. And after 300 seconds, we sort of pulled the plug and said, okay, if you can't find it, let's end the trial. And we were hoping for a really dramatic effect. Unfortunately, it wasn't quite that simple. So the first thing to say is the way that BLADE is constructed, every time it reads a barcode, it's corrected. I mean, I haven't seen it make a mistake in a very long time, and that's part of the way that the algorithm is designed. So it may actually hesitate before it's sufficiently confident. And there are histograms down here of search times that sort of suggests that the search is a little bit faster with the feedback on. But the real question is, does the feedback actually help or not? Statistically, there's some evidence. You know, we have a p-value of 0.056, which is not what you're hoping for. You always want, you know, lower than 0.05. It might be construed as a trend. So there's more work to understand this, and this kind of issue will come up in the other applications Roberto talks about next. The highlights, though, just to point out, the subjects clearly preferred the feedback. At least they said they did. No reason to believe that they were lying, and part of that might just be a psychological effect of, well, I like having feedback, even if it's not always helpful. The study is flawed in that there's a huge amount of variability between different subjects, and perhaps a different analysis in the future could sort of uncover that. And 5 subjects is fairly small. And the conjecture I have is that part of the reason that the feedback is not necessarily improving things a ton is that the feedback is noisy to some extent. So sometimes you have false positives hallucinating a barcode when it doesn't exist, or false negatives not seeing it, and that limits its effectiveness. So that's something that a theme that will reappear.
Thanks, James. So let me talk about the second application. So this has to do with guidance to a target, and think of this. Imagine there is a sign on the wall with some text, and you may have something on your cell phone similar to Text Detective, a text recognizer that can tell you, look, there is something interesting over there. You need to get close and take a better picture once you're closer so you can read the text. If you think for a moment, that could be similar to the paradigm of, I have an object recognizer, now I want to go and grab this object, and I want the camera to lead me towards the object so that I'm going to be able to grab it at some point. So the goal here is to be able to take a well-framed picture of a target at good resolution, which is kind of like a common denominator of many of the things we're talking about today. Now, if you want to do that, if you want to study how users interact with the machine for that, you need to specify the type of algorithm you have for your object detection. And of course, there are multiple of these, and we really wanted to abstract from that. We want to concentrate on the user. So what do? We cheated. And I'm Italian, I can do that. So we generated our own special target, which is shown here in a picture. It is a color pie with 4 colors, just made for our own consumption. And we did some software on the phone that, given that it is such a special target, the detection is almost perfect, very reliable, very fast, and etc. I'm not trying to say that the same software will work for anything else. It works for this target for this particular study. Okay, so we solved the problem. We can abstract from the technical part, concentrate, and see how people can use this system that recognizes this target to get closer to the target and, for example, take a better picture. Now, in the next slide, I'm going to show you a movie with a blind woman operating a cell phone that recognizes this target. We recognize a target of 15 centimeters of diameter of up to 3 meters of distance. And you'll hear some beeping. When the cell phone beeping means that it is detecting the target within the field of view. And so here is an example. She's holding a dog guide. We quickly realized that there are 2 phases to this process. The first phase is search. Let me make sure that this goes. So search means that you need to look around in your environment until you find a target, if there is a target inside. So that's what she's doing this moment. And the cell phone is beeping. So she found a target, now she's walking closer to the target. That's the second part of the process, which is guidance. You want to be guided towards the target, basically following your own arm, which clearly needs proprioception. Now what I found out is sometimes, like in this very moment, the target gets lost in the process. At some point you're walking, but your camera is pointing to something else. It doesn't beep anymore. You don't have the target in sight. Now this woman was very good. She was able to get the target, but sometimes we have a situation of people getting very close at some point, losing the target, and that was a very frustrating operation. Now, the reason for this is that cameras have limited field of view, right? So if you point it in the wrong direction, at some point, don't see what is supposed to be there. So we thought, well, perhaps we can improve this by increasing the field of view of the camera. And we did it. So how can I increase the field of view of my iPhone? I buy a little add-on, for example, a company named PhotoJojo makes that doubles up the field of view of your iPhone. Makes you take panoramic, well, kind of fisheye pictures. So our goals in these experiments were to test the validity of this assumption that increasing the field of view for this type of guidance tasks can be useful. And we did a testing with or without this add-on. Keeping in mind, though, that if I increase the field of view of my camera, maintaining the same resolution, the same number of pixels, I am reducing the angular resolution. Basically, another way to say that, if I take a picture of the same object from the same distance with a camera and with a camera with a large field of view, the second picture shows the object smaller. Okay? The other thing we wanted to check is how important is a fast frame rate. Now, this system is pretty fast. On an iPhone, it goes up to between 3 and 10 frames per second. But of course, if I had something a little bit more complex, it might take more time. If I had something in the cloud, it might take more time. If I had crowdsourcing, it's going to take more time. Okay, so clearly, if I take a picture a minute, I can't really do a decent guidance. So what is the breakdown point? Well, we tested it, for example, with a system that takes a picture every 2 seconds to see if this is going to decrease our performance. Now, user interface, first about the experiment. We had 18 blind participants on 2 different sites. It was a within subject test. Each participant, one of whom is in this room, by the way, tested with narrow and wide field of view and with fast and slow frame rate. And the goal of this test were starting from the same starting point, which is about 1.5 meters from the target, somewhere where the cell phone will beep right away because it sees it. We asked the participant to walk towards the target and to take a good picture of it. Basically, move the camera so that the camera will be in a position where you can take a good picture, where a good picture means that the whole target must be in sight, that needs to be well centered, and it must have a minimum resolution. Basically, you need to occupy a certain amount of pixels. Now remember that with a certain field of view, you need to get closer to take a picture of the same number of pixels. I'm showing 2 pictures here of the target. The target looks of the same size in the 2 pictures, and the first one, it was taken with the regular field of view of your iPhone at 57 centimeters of distance. The second one was taken at a closer distance, 30 centimeters of distance, with a wide angle. And these were actually the threshold distances for success in our experiment. User interface, like I said, is pretty minimalistic, and that comes from past experience. We have a similar system. We could try to give a lot of information to the user, but then we had a problem with the cognitive load, and it started confusing which signals which information. So we basically give information about centering with synthetic speech that say rotate the cell phone left, right, up, and down. And about distance, basically we have a different beeping rates depending if you are closer or farther away than 50 centimeters. And here I have a little video of a blind woman who is in front of a wall with multiple markers, but in fact each one of these markers is a little bit different from the other, and the software has been as a flag that says look for just one of these markers. You will hear, although there is a lot of background noise, some of the directions given by the system, how this woman following the direction is eventually able to get a good picture. Turn up.
Turn left. Turn up. You have reached the target.
You have reached the target. All right, so what are the results? What did we expect to see? We expect to see that with a wider field of view, we would have fewer these target losses that I talked about, and therefore better performance in terms of the average time to take a good picture. Also, we expected that if I lower the frame rate, the performance will go worse. What have we found? Something interesting. If I increase the field of view, I do have fewer target losses, but the performance did not increase. They actually, in this case, kind of decreased. Also, with lower frame rate, I get worse performance only with a narrow field of view case. Now, the second case is easy to explain. Imagine if you're taking 2 pictures as you're rotating the camera with a wide field of view, there is a lot of overlap between these 2 pictures. So probably don't need such a fast process frame by frame unless you really move the camera real fast. Now the first one, we're still trying to discover a little bit. It might have to do with length, angles, and etc. But I don't really want to talk about that. It's kind of an open issue for us, quite a surprise. I want to talk briefly about the third application that has to do with mobile OCR. There's been quite a bit of talk about mobile OCR here. Now, I'll make a bold statement. I think the mobile OCR works pretty well. Now, Peter might say, well, 85%. I don't know. When I try it, I'll say, okay, it's not perfect, but it's fairly good as long as, of course, we can take a good picture of the document. And that is the difficult part, as I hear very often from people who use these mobile OCR systems. How can an automated system help me take a good picture of a document? Where there are 2 paradigms, I think, in mind. One is what I call the guidance paradigm, a system that helps you actually move your hand so that you will take a good picture. And a little bit of that is in the KNFP reader's field of view report, if any of you has ever tried it. Basically, you take a picture of the document and then you wait for a few seconds and then the system tells you, oh, I only see 80% and it's skewed in this way and etc. So if you held your hand steady and you listen to the report and you think about it, maybe they can help you. It tells you you have to rotate your hand or do something like that. The other possibility you have is what I call opportunistic shooting. That is, you hover your phone over the document, the system keeps taking pictures, and at some point there's going to be one picture that is really the right one that contains the whole document, good resolution, and that is the one that passed on to this lower OCR. Now, Say Text, which is a free iPhone app, has a very, very simple way to do that. Basically, it looks for edges to the documents. When it finds edges that look like a square, it thinks, oh, I found a document, take a picture of that. Text Detective of our friends here, Blind Sight, detects lines of text, and again, quickly goes through frames until it picks one that it thinks is the right one. Now, we wanted again to try to ask ourselves these questions. If I had a system that can give me real-time guidance, I'm not going to tell you how I'm going to do it, but suppose you built it. It's perfect. It gives you good guidance. How well would it work? Would it really help you take better pictures? How would it compare to a probably simpler opportunistic shooting type of system? And the second question we asked ourselves is, if I have an automated system like that, will it help me learn how to take better pictures? Because in theory, if I learn how to take a good picture of a document, then I don't need any of this. I could probably have somebody teach me how to do that, but maybe an automated system can be good for that. Now, as I told you last time, we cannot cheat by using the thing, so we kind of like the idea, and we cheated this time too. And we invented this system here. Basically, for our experiments, rather than having a sheet with text printed on it, we have pattern printers on a sheet of paper. And these patterns are augmented reality patterns. These are open source things, such that if I take a picture of one or more of these patterns, I can, with good precision, understand the pose of my camera, that is, the 3D location of the camera and the orientation of the camera. Now, you can imagine that if I can do that, if I can track the pose of my camera with the system here, which is again only used for experiments, I should be able to infer whether a certain pose is a good picture, is a good pose, such that it's a compliant pose, as I explained, allows me to take a picture. And if it is not, it should be able to give me indication of how I should move the camera so that I can take a compliant pose. Well, a compliant pose is such that the picture taken from there takes the whole document, all four corners are visible, and all characters in the document have decent resolution. All right, so let me show you an example of a simple guidance system built on this. You will hear some very ugly synthetic speech. 2 people in this room tried this. We had 12 actually blind testers here. You will hear some pretty ugly synthetic speech that gives direction like move up 5 and forward 2 or things like that. And the user here is moving a cell phone, following that over the document. Let's see how it works. Post-compliant. So, thanks, James. So in this case, the user was able to follow the guidance. You need to reduce this a little bit, James. The guidance given by the system, and eventually get to a post-compliant, where a good picture would have been taken. Now, let me jump directly to the conclusions. I'm not going to describe the experiments and etc. These were between subject experiments, something I regretted very much doing, but oh well, you can't go back and change your methodology. So some of the preliminary results we found out. First, some users are really bad at this, and some users are really good. The variance is huge, probably something that James maybe also has found. Some users simply cannot take a picture of a document, a good picture, compliant, even if we tell them, look, you just need to have the phone about 1 foot, 1.5 feet over the document. They just can't. And even with the guidance system, they wouldn't be able to do that within a certain maximum time. The second thing that we found that was a little bit of a surprise, and we're trying to investigate why, is that if I use a guidance system, or if I use my opportunistic shooting, I just hover the camera over and somebody sits there and say, oh, I took a good shot. It seems like the average time to success to get to a compliant pose is comparable. That was a surprise. We thought guidance would definitely be a winner. Well, that could be that our guidance system sucks. Maybe the interface was not good at all. Or it might just be that if you just hover the camera and you have a system in real time that exactly know when there's a good point, you may be lucky enough to get the right snapshot. The last thing that we found out is that by doing pre-intervention, post-intervention test without the system, and in between the intervention test with the system, people did in fact learn to take better pictures. There is statistical evidence that the system may help you to learn to take better pictures of a document. Okay, this is basically my last slide to conclude. I think kind of like I'm trying to find common denominators here. In my opinion, and I hope it's James' opinion too, because I have the microphone there. So there are multiple parameters in this issue of camera-based system. One is the field of view resolution of the camera, this very technical issue. One is the interface with the user. One is my own perception dexterity ability. One is the frame rate. These guys cannot really be taken independently. If you change one, this is going to affect all of the rest. Or better, you need to consider multiple of these as you try to optimize your system. And this is the last slide of acknowledgements for our grant, and I am done.
Any questions before the break?
It's less a question, more of a comment about your last graph that you put up about the field of view, the interface, and proprioception, and the frame rate. And we have found the same thing, and especially with Money Reader, when it started recognizing things at real time, because we had earlier models that were not real time. As soon as it started becoming real time, people's hands started going immediately to the bill, and they started understanding how the camera works. And so that diagram is great.
Thanks. Okay, the question.
So focusing seems to be an issue, right? You told something about like that users don't hold the phone at the right distance. So would like light field photography be a solution to the problem?
So focusing was not an issue in any of these problems.
Just getting things in the field of view.
Oh, okay.
Another question?
That's not clear. Or the next question.
Just a couple of questions. One is that the users who couldn't really do it very well, was it hand jitter or misorienting the phone? And then the second question is, in the big picture, it's a fairly hard sort of AI problem, isn't it, to figure out what the optimal compliant view is? I mean, if you have text with a weird layout, the compliant view might be very different than a standard, I don't know, business card or some other standard text layout.
Thanks. Does it work? Yes. Thanks for the question, Gordon. So the first question was about what would the users who were not good, why were not good? You know, I can tell you, the users who were good, they had a method. And it's not clear to me, it is something that I need to do some post facto from all of the interview eventually people, whether it is on the fact that these people, due to the fact that these people have used these methods before, some of these people have used VOCR before some others, and maybe they have learned a method. I noticed that some, in this and other experiments, we learned that for some blind people, holding a cell phone straight is a challenge. Okay? It's not easy at all. Holding a cell phone parallel to the desktop as it should be, a challenge. Some people would raise the phone and immediately orient it in a strange way. But even though the system would try to help them to say, straighten up the cell phone, somehow that wouldn't work. The second question you had was, well, how difficult or easy is to understand whether a document is compliant. Remember, I told you, if we had a perfect system, and I'm not going to tell you how we do it. In fact, we don't. We are cheating because we have a system that is able to obtain the full 3D geometry of the camera because we're using a special pattern. Now, of course, the question is, and our mental thought was, let's first try with this. Let's see what we learn from this. And if this confirms the guidance could really be something good, let's move towards trying to design a system that can do guidance on a real document, which we haven't done yet.
Let me just add to the first question, who is sort of good at doing these tasks and who is not so good. I mean, one thing that also became clear is that training is incredibly important. Some people may not need training, some people may benefit enormously from just a little bit of training. And you know, it was hard to standardize our training perfectly. We attempted that in some ways, but I think our training got better as we saw more subjects. And so I think fitting the training to the person is a huge thing that needs to be explored more. And I'm sure Laura Lakova has a lot of things to say about that too. Yeah, let me get the microphone.
Noel Runyon. And I shouldn't say that I was one of the subjects, should I? But
I didn't say
what I found out was that there were two navigation direction needs. One was when I'm actually working with the unit, trying to do pictures of pages and stuff in ongoing reading. The other is in the upfront training, and having a machine that responds quickly with maybe analog type feedback or something to be used in training just to help you develop your techniques. Like I was just trying to figure out how to get the camera level, and what that was something where having the machine have a different mode of feedback for training might be very helpful in contrast to the mode that's used when you're actually doing work with it.
I think that's a great idea. I think it's an excellent observation, and in fact like I said, I don't want my past experience to have an interface that gives you too many things, because I think people get confused easily, but as you say, perhaps during the training, as I'm learning that and I'm taking my time, that might be the right thing to do.
All right.
Shall we wrap up? Yes.